All right, hello everyone. Good evening from Hefei City, China. It's a pleasure to participate in this seminar series through a talk entitled Seismic Faulting in the Moroccan Rifted Margin, Active Basin Inversion of the Moroccan High Atlas. I'm Hamza Skikra. I'm a postdoc fellow in geomechanics and structural geology at the University of Science and Technology of China, working under the supervision of Professor Chao Dongma. And today I would like to take you on a journey through a truly remarkable case of basin inversion, taking the Moroccan High Atlas as a natural laboratory, which is widely recognized as a world-class example of inverted rift system. So before we dive into the details of this presentation, let's just give an introduction about the study object, which is the High Atlas, in order to position it regionally. I will start by map A here in the bottom, which indicates the location of the intraplate fold and High Atlas fold or Atlas system fold and thrust belts in the Western Mediterranean domain as part of the North African Alpine orogenic system. Map B indicates a regional geological map of North Africa. We can see the reef and till collision belts in the north along the plate boundary between Africa and Europe. And southward, in a purely intraplate position, lies the Atlas system, which extends from the Agadir Sawera region in Morocco all the way to Tunisia through the east. In Morocco, the Atlas system branches into the northeast trending Middle Atlas and the east-west to east-northeast trending High Atlas. Both of these systems are actually Mesozoic rift basins that were subsequently shortened and uplifted, or in other words, inverted during the Alpine orogeny since the late Cretaceous until the late Cenozoic. So this leads us to some core questions of this presentation. Is the inversion process that caused the formation of the High Atlas fold and thrust belt still actively shaping the landscape and crystal deformation today? What about the driving mechanisms of the present-day seismotectonic activity in the High Atlas? How does other factor like structural inheritance or mantle dynamics control the present-day seismotectonic activity? And what can we learn from the 8 September 2023 Al House earthquake, given that this is the most powerful earthquake ever recorded in the High Atlas and also the recent earthquake reported in the area? So, right. So the following figures show a closer view of the main structural features of the High Atlas. In details, the cross-section here in the bottom demonstrates an overall doubly virgin geometry or structure of the range, with the central High Atlas in the case B being marked by thick Mesozoic folded series and diaperic structures, while the western High Atlas in the case A is marked by this axial zone here where basement blocks are exhumed and uplifted through these basement folds, such as the famous example of the so-called teasing test fold zone that we can see over here. And I'd like also to mention that this portion, this axial zone of the Western High Atlas, actually represents the highest part of the entire orogenic system in North Africa. And it's also the locus, as I just mentioned, of the most powerful earthquake ever reported in the area. So in the next slide, we'll try to focus a little bit on this portion of the High Atlas. So before moving on, I would love to mention another important aspect about the geodynamic patterns of Northwest Africa and the Atlas system. Several geophysical studies showed the presence or demonstrated the presence of this northeast-southwest trending corridor where the lithosphere-asthenosphere boundary is quite elevated, as we can see here from this profile. We notice that the lithosphere-asthenosphere boundary reaches about 80 to 90 kilometers beneath the High Atlas, a feature that will become relevant later when we discuss the deep controls on seismogenesis in the High Atlas region. So now we can ask, is the High Atlas system is still active, or in other words, is the basin inversion still operating in this area? Evidently, from these maps, we can see that the High Atlas is seismically active, while the activity is actually quite moderate, with events rarely exceeding magnitude 6 in the range. To better understand the origin of these seismicity, we derived here the stress pattern causing this seismic activity by compiling the available focal mechanisms in the area. And here we obtain a transpressional stress with northwest, southeast striking sigma 1 and vertical sigma 3. We can also notice that the stress ratio that we obtain here for these compilation is quite low, which is explained, of course, by the coexistence of reverse and strike slip faulting. So here in this map, placing these results into a broader regional framework, we find a remarkable consistency between the stress pattern in the High Atlas and the entire North African orogenic system. So this suggests that the seismicity that we observe here in the High Atlas is actually the response to a first-order stress field related to the ongoing oblique convergence between Africa and Eurasia, or more precisely between the Nubian plates and Eurasia. So I'm sorry. Right, so this ongoing activity actually is manifested by the dramatic 8 September 2023 El House earthquake with magnitude 6.8. This tragic event claimed more than 2,800 lives in the High Atlas, making it the most powerful earthquake known to date in the High Atlas. Of course, in terms of magnitude, these images over here show some example of damages in villages near this epicentral area. From this intensity map, we can see that the damage extended, for example, in other cities outside the range, like Marrakesh and Taroudannt, north and south of the High Atlas. The following table presents an initial compilation of different parameters of the El House earthquake published by Yeki all in Seismic Record in 2023. It highlights two critical aspects regarding this event. Firstly, as we can see here from the depth, we can notice that it extends surprisingly deep, potentially into the lower crust of this portion of the High Atlas. Secondly, fault plan solution showed the presence of two potential causative faults for this event. One is steeply dipping and one is gently dipping. However, in this area, there is no evidence of surface rupture associated with this event because this earthquake occurred mainly by a blind fault. So for months after the aftershock, a lot of controversy was surrounding the causative faults for the El House earthquake. To further understand the seismotectonic setting of this event, we conducted a multi-approach analysis combining seismicity and geodetic observations. Looking at decadal seismicity here in the epicentral area or near the epicentral area of the Western High Atlas, we can show that there is a moderate background for the 1 decade preceding the main shock, with events really exceeding magnitude 4, as we can see here. The plot in the right illustrates the surge in seismic activity, as we can see here, following the main shock, which notably affected the entire Moroccan seismicity rate. These observations or these data was used to map the B-value, which is a parameter well established in literature to be inversely related to differential stress for the period from 2015, as we can see here, until late 2023. We observed that the epicentral area here corresponds to a low B-value of about 0.8, which is below the global average, which is known to be close to 1. This pattern may suggest a localized stress concentration in this area for the time preceding the El House earthquake. Secondly, we turn to geodetic record. This map shows a GPS velocity field relative to fixed Nubian plates. Despite sparse network that we have here in Morocco and the inherent uncertainties, of course, the pattern is somehow clear. As we can see from the atlas, actually the velocity field in this region is remarkably slow. In general, is below 1 millimeter a year. Then we try to quantify the shortening rate in different segments of the High Atlas by quantifying the evolution of the distance of these different baselines through time. We will focus on these FSSM2 baseline over here, which is roughly orthogonal to the Western High Atlas, and it's close to the epicentral area of the El House earthquake. Interestingly, we were not able to discriminate clear shortening estimates in this area. We can see here that the value is very small. However, something important was obtained. We can see here in this station between these two FSSM and 2, which is UCA, is located in the axial zone of the Western High Atlas, specifically near the so-called Tizian test fault that I mentioned in the beginning. And we can notice that the uplift reported in this area is remarkably important compared to the reported shortening in this. region. So we interpret this as the important role played by basement faults in accommodating the present day deformation of this part of the high atlas. This is also important as this could make this teasing test fault as a good candidate for the El House earthquake generative faults. So this actually brings us to a core geomechanical challenge regarding the genesis of the El House earthquake. Firstly, let's recall the seismotectonic pattern of this event. As I previously mentioned, the fault plan solution indicates the presence of two potential plans. One is northeast, northeast, southwest, west, southwest striking and steeply dipping faults, and the other is northwest, southeast, steeply dipping, and it's also marked by gentle dip. Few weeks
Hamza,
after,
you've used 10 minutes now, okay?
of course, I'm close to the end. All right, so a few weeks after the El House earthquake, this geomechanical assessment was published by Lewandowski in Seismic Record, in which he used this stress sensor with roughly north-south sigma 1 and vertical sigma 3 to estimate the fault slip potential of the different faults in the area in order to discriminate between the focal plans and the auxiliary plans in the high atlas and to determine which one of these two plans could be the causative for the El House earthquake. As we can see from the Mohr circle, considering a standard failure envelope with friction coefficient of 0.6, the gently dipping El House fault plan appear as the most potential faults, causative faults for this event. However, the observation of aftershocks for several weeks after the main event indicate that the so-called teasing test fault is actually the most probable causative fault for this event. So we have like this difference or contrast between what we can predict from geomechanical model and the observations, which allow us to reconsider or reevaluate the frictional properties of this fault zone here in the high atlas. So taking this into account together with the depth of the event, as I mentioned earlier, this led several authors to invoke the role of mantle dynamics in generating such events. However, how these mantle processes could interact with the plate-driven contractional deformation that we obtain, for example, from the inversion of focal mechanisms, is still ambiguous, and further investigations needs to be conducted to understand this link. So to sum up, the High Atlas is an exceptional natural laboratory that illustrates the tectonic complexity of inverted rift system. The present-day analysis showed that the High Atlas seismicity is driven by first-order stress field related to the convergence between Africa and Europe, which was operating since the late Cenozoic until the present day. The range deforms under moderate seismicity and very slow geodetic velocity field. However, it has the ability to generate a powerful and destructive earthquakes, such as the example of the El House event. Last but not least, the results emphasize the important role of structural inheritance, particularly the role of the teasing test fault zone, and the potential role also of the mantle dynamics, and how these can be or should be considered as critical parameters in any future seismotectonic assessment, either for the High Atlas or other similar inverted rift systems worldwide. That was all for my talk. Thank you very much.
Thank you, Hamza. That was a good talk. Any questions for Hamza? If you have any questions, you can just unmute your microphone. All right, Derek has one.
Thanks, nice talk. Are there any constraints from INSAR on the kind of deformation pattern and potential geometry of the fault plane from the El House earthquake?
Yes, indeed. There are actually plenty of research that were published recently. And the majority of these analyses, they indicate that the steeply dipping fault is actually the most probable causative fault for these events. Yes, actually, there are several studies, and as I said, most of them because there was an initial study used in INSAR few weeks after the El House earthquake was published, and it suggested that probably it could be like this gently dipping, but majority after this research So they indicate that the simply dependent fault is the most probable causative fault, especially that they combine the INSAR insights with the aftershock patterns that were not available in the beginning, in the first weeks in the area.
Okay, thanks.
There, Sasha.
Yeah, thanks for this nice talk. I'm wondering about this Tizine test fault zone that you highlighted at 2 occasions, and you mentioned that this is an inherited fault zone from the rifted margin. Could you maybe explain a bit what the original position was in the rifted margin and how it evolved through time?
Yeah, of course, that's a very important question. Actually, this is commonly considered in literature as a long-lived fault that was operating since maybe the Precambrian times, and it was also active during the Variscan, so it has like a long-lived structural or tectonic history. During the rifting phase, it was also very active because I'm sorry, I don't know if it's not very well shown here, but you can see this small portion of Triassic deposit over here. So along these faults in the Western High Atlas, we can see the relics of these Triassic basins near these faults. So we can say that actually it was very active and it was a major player during the rifting phase and the opening of the High Atlas basin.
Okay, thanks.
I can ask a question. So I noticed that in your B-value map, you have some moderate B-values closer to the coastal plain, like further west. And I was wondering if there's anything, like the one at latitude between
This one?
north of, slightly north of that.
Here?
No, to the right, further to the right, not too far, around longitude, just west of longitude 8.
West 8 here? No?
Yeah, if you're moving north a little bit, there's a cluster of blue. Yeah, right there. Yeah, because I wonder if you have any insight into what the seismic sources for those might be, because they have lower B values, which means you have slightly moderate sized faults there that are causing those earthquakes, right?
Yes, I agree with you. However, actually, we did not go into these details in this study. And currently, we have a PhD candidate that is working on the B-value analysis on the entire Moroccan domain. And in this study, we're trying, as you mentioned, to see all different patterns, different anomalies that we can observe. So your remark actually is very interesting, but however, in our study, we try to focus more on this region near the epicentral area. So we did not have the chance to delve into details in other segments of this map.
And just to clarify, there's not much that is known about seismic sources closer to the coast. Like
I don't think so.
northwest.
I don't think so. Yeah.
Okay, great, thank you. All right, I think we can move on to our next speaker, Barney Wu.
Can I ask the questions actually?
Okay, quickly, because you're cutting into your time.
Yeah. I was wondering, like this, are you suggesting this uplift is causing by these earthquakes? I mean, like a lot of these earthquakes, actually, those uplifting are accommodated by this type of earthquake. Is that the argument?
Okay, actually, this is an interpretation of this Chinese group. It was published in GRL. It's not my interpretation. I don't think that there are some strong evidence because this is still very speculative, given just the interpretation, the location of the atlas in this area where we have a lab, but it's not that clear. What we know is that, yes, it is this steeply dipping fault that is like the most probable and potential faults that caused the Al Hawz earthquake. How can this mantle dynamics be involved in this region? Maybe by reducing the friction of these faults, but it's still not that clear for me, my opinion.
Yeah. Okay. Thank you so much, Hamza. It's a great talk.